Welcome to Strange America. There are a lot of things in everyday American life that we use without thinking twice about them, and tap water might be one of the best examples. You walk into the kitchen, grab a glass, turn the faucet, and clean water comes out almost instantly. It feels simple, maybe even boring. But that glass of water may have traveled many miles before reaching your sink. It could have started in a river, a lake, a reservoir, or deep underground. Along the way, it may have passed through giant pipes, pumping stations, treatment tanks, filters, chemical systems, storage towers, and miles of underground water mains. All of that work happens quietly in the background, so most of us never notice it. The faucet gets all the credit. So imagine an ordinary morning somewhere in America. Maybe you are in a house outside Dallas, an apartment in Chicago, or a small neighborhood in Ohio. You turn on the shower, start the coffee maker, rinse a plate, or fill a bottle before leaving for work. In just a few minutes, you may use several gallons of water without ever wondering where it came from. But before that water reaches your home, a local water system has to find it, collect it, clean it, test it, store it, pressurize it, and move it through a huge network of pipes. And here is the strange part. Much of that system is completely invisible. Roads, houses, stores, parking lots, and sidewalks sit above an underground network that quietly keeps entire cities running. So when you turn that little metal handle in your kitchen, you are not simply opening a faucet. You are opening the final door of a journey that may have started days, weeks, or even months earlier. The first question is simple. Where does city water actually come from? The answer depends on where you live. Some American cities pull water from big rivers. Others depend on lakes or man-made reservoirs. Many communities use groundwater from wells that reach into underground layers of rock and soil called aquifers. And some places use a mix of all of these. New York City, for example, is famous for bringing much of its water from protected watersheds and reservoirs far north of the city. Parts of the Southwest depend heavily on rivers, reservoirs, and groundwater. In many smaller towns, deep wells may do most of the work, so there is no single American water source. The country is too big, too dry in some places, too wet in others, and too geographically complicated for one system to fit everyone. Let us start with surface water, because this is the easiest kind to picture. Rain falls, snow melts. Small streams feed larger streams. Those streams flow into rivers, lakes, and reservoirs. Somewhere along that route, a water utility may have an intake structure designed to pull in raw water. Raw water is simply water that has not been fully treated yet. It may look clear, but that does not mean it is ready to drink. It can contain dirt, tiny pieces of plants, microorganisms, minerals, natural organic material, and pollution washed in from roads, farms, lawns, or industrial areas. Nature is very good at making water, but nature does not package it with a little label that says, "Ready for your refrigerator." At the intake, the system usually begins by keeping out the big stuff. Screens can block sticks, leaves, trash, fish, and other objects that definitely do not belong inside treatment equipment. Think of it as the first security checkpoint. A plastic bottle floating in a river may be annoying, but it becomes a much bigger problem if it gets sucked into a pump that costs more than your house. After screening, big pumps move the water toward a treatment plant. In some systems, gravity helps carry the water. In others, powerful pumps do the heavy lifting. Either way, the goal is the same: get a huge amount of raw water from the source to a place where it can be cleaned in a controlled way. Now the water treatment plant enters the story, and this is where the process becomes much more interesting. A modern plant is not just one giant filter. It is usually a sequence of treatment steps, each designed to remove a different kind of problem. One common early step is coagulation. That word sounds like something from a science exam you hoped never to see again, but the basic idea is simple. Very tiny particles in water can be too small to settle out on their own. Treatment operators add chemicals that help those particles lose their electrical stability and begin sticking together. Instead of millions of tiny invisible specks floating separately, they start forming larger clumps. Next comes flocculation. The water is mixed slowly so those tiny clumps can bump into each other and grow. The larger clumps are called flock. They can look like little cloudy snowflakes drifting through the water. This step is gentle on purpose. If the water were mixed too violently, the flock could break apart again. So the plant carefully stirs the water, giving particles time to gather together. It is a little like trying to get everyone at a crowded party into organized groups without starting a fight. The goal is not excitement. The goal is cooperation. After that, the water often moves into large settling basins. Here, gravity gets a chance to help. The heavier flock slowly sinks to the bottom, carrying dirt and other suspended material with it. Equipment removes the settled material, while the clearer water near the top moves forward to the next stage. This is called sedimentation. It is one of those steps that sounds almost too simple, but it can remove a large amount of material before filtration even begins. Plants are designed this way because it is much smarter to remove a heavy load early than to force the filters to do everything later. Then comes filtration, one of the most recognizable parts of water treatment. Water passes through layers of material that may include sand, gravel, activated carbon, or other specialized filter media. These filters catch smaller particles that made it through the earlier steps. Some systems use advanced membrane technologies as well. The exact design varies from plant to plant, but the principle is familiar. Water moves through something that lets the water continue while trapping unwanted material. If your home coffee filter catches grounds before coffee enters the pot, you already understand the basic logic. Of course, a municipal filter is operating on a completely different scale and dealing with much more than coffee grounds. But clear water is not automatically safe water. Microorganisms can be invisible, and some of them can make people sick. That is why disinfection is a critical part of public water treatment. Utilities may use chlorine, chloramine, ozone, ultraviolet light, or combinations of these methods depending on the system. Chlorine has been widely used because it can kill many harmful microorganisms and, importantly, a small residual can remain in the water as it travels through pipes. That remaining disinfectant helps protect the water from microbial growth after it leaves the treatment plant. Treatment is not just about cleaning water once, it is also about protecting it during the trip. This is also where people sometimes notice a slight chlorine smell or taste in tap water. In many systems, that does not mean someone accidentally poured swimming pool water into the main line. The amount used for drinking water is carefully controlled and monitored. Utilities have to balance effective disinfection with taste, odor, chemical byproducts, and other water quality requirements. Operators constantly test and adjust the process because source water can change. Heavy rain, drought, seasonal algae, temperature, and changes in river flow can all affect what arrives at the plant. A treatment plant cannot just use one setting forever and hope for the best. Water chemistry matters too. Utilities may adjust pH, alkalinity, or corrosion control depending on the characteristics of the source water and distribution system. Why does that matter? Because water does not stop interacting with things after treatment. Once it enters pipes, its chemistry can affect metal surfaces, mineral buildup, and the way certain materials behave. Proper corrosion control is especially important because the distribution system may contain older service lines, plumbing materials, and fixtures. The water has to be treated not only for what is in the source, but also for the long trip through infrastructure before it reaches your glass. Now let us say the water has finished treatment and passed the required quality checks. It still has a long way to go. The next challenge is moving it across a city while keeping enough pressure for homes, businesses, schools, hospitals, fire hydrants, and high-rise buildings. Water leaves the treatment plant through large transmission mains. These are the highways of the water system. From there, the water enters smaller distribution mains, then even smaller service lines that connect individual buildings. By the time it reaches your kitchen faucet, it has traveled from giant public pipes into the private plumbing inside your home. Pressure is one of the hidden heroes of this whole system. Without enough pressure, turning on the faucet would be a disappointing experience. Maybe you would get a weak trickle, maybe nothing at all. Water utilities use pumps, elevated storage tanks, reservoirs, and pressure zones to keep water moving. The classic American water tower is not just a piece of small-town scenery with the city name painted on the side. It stores water at a height, and gravity helps create pressure in the system. When demand rises, stored water can flow into the network. When demand falls, pumps can refill the tank. That giant tower you pass on the highway is quietly helping someone take a shower. Cities also have to deal with elevation. Water pressure that works perfectly in a low neighborhood may be too weak for homes on a hill. On the other hand, too much pressure can damage pipes and plumbing. So large systems may divide the city into pressure zones. Pumps and valves help manage those zones, so water arrives with enough force but not too much. In a place with hills, valleys, tall buildings, and growing suburbs, this can become a complicated engineering puzzle. Your faucet does not care about any of that. It simply expects water every time you turn the handle. Demanding little device. Storage is important for another reason. People do not use water evenly throughout the day. Demand often rises in the morning when people shower, make breakfast, and get ready for work or school. It may rise again in the evening when people cook, wash dishes, do laundry, or water lawns. A system has to handle these peaks without building every pump, as if the entire city will turn on every faucet at exactly the same second. Storage tanks and reservoirs help smooth out those changes. They also provide emergency reserves for situations like fires, equipment problems, power issues, or temporary interruptions at the treatment plant. Fire protection is a major reason municipal water systems need strong capacity and pressure. Fire hydrants are connected to the same general distribution network that serves homes and businesses. When firefighters open a hydrant, they may need a very large flow of water quickly. That demand can be far greater than normal household use. Engineers have to design pipes, pumps, tanks, and pressure zones with those emergency needs in mind. So the water main under your street is not just there for showers and pasta. It is part of the city's firefighting system too. Then, there are the pipes themselves, and this is where the underground world becomes surprisingly huge. American cities have thousands upon thousands of miles of water mains. Some are relatively new, others have been underground for many decades. Materials can include ductile iron, cast iron, steel, concrete, copper, and various plastics depending on the age and purpose of the line. These pipes are buried beneath streets, sidewalks, yards, and utility corridors. Most of the time, nobody sees them. But when a major water main breaks, suddenly everyone in the neighborhood becomes very interested in municipal infrastructure. A broken water main can happen for many reasons. Old pipes can weaken, soil can shift, freezing temperatures can stress materials, construction equipment can hit a line, pressure changes can contribute to failures. In some older cities, utilities face the difficult job of replacing aging pipes while keeping water service running for millions of people. That is expensive, slow, and disruptive. You cannot simply close an entire city for 6 months and announce, "Sorry, we are replacing the plumbing." Repairs often happen section by section, street by street, sometimes in the middle of the night to reduce traffic problems. When crews repair a main, they have to think about more than stopping the leak. The system must also be protected from contamination. If pressure drops too low, outside material can potentially enter damaged pipes. That is one reason communities sometimes receive boil water notices after major breaks or pressure losses. A boil water notice does not always mean dangerous contamination has been confirmed. Sometimes it is a precaution while the utility tests the water and makes sure the system is safe again. The notice is basically the city saying, "We are checking everything, so use extra protection for now." Water utilities also test water throughout the distribution system, not just at the treatment plant. Samples may be collected from different locations to check disinfectant levels, bacteria, chemical characteristics, and other regulated contaminants. Operators monitor tanks, pumps, pressure, flow, and water quality data. In larger systems, much of this information is tracked electronically around the clock. If something changes, staff can respond. The system may look quiet from the street, but behind the scenes, there are people watching numbers, adjusting pumps, checking samples, repairing valves, and trying very hard to make sure you never have to think about them. Now let us follow the water all the way to your property. Somewhere near the edge of your lot or building, a service line connects the public water main to your home. In many places, a water meter measures how much water you use. The exact ownership boundary between the utility and property owner varies by location, but once the water enters private plumbing, the condition of that plumbing becomes important. A city can deliver high-quality water to the property, but old pipes, neglected fixtures, stagnant water, or poorly maintained treatment devices inside a building can affect what comes out of the faucet. This is why water can sometimes taste different in an older house than it does in a newer apartment across town, even if both receive water from the same utility. Plumbing materials, pipe length, water temperature, how long the water has been sitting, and household filters can all change the experience. If a faucet has not been used for a long time, the first water out of the tap has been sitting inside the building's plumbing. Running the cold water for a short time can bring in fresher water from the service line, especially after long periods of non-use. Groundwater systems follow a somewhat different path. Instead of pulling water from a river or lake, a well draws water from underground. Rain and snow can slowly seep through soil and rock, eventually reaching water-bearing formations. That natural movement can filter out some particles, but groundwater can still contain minerals, metals, naturally occurring chemicals, or contaminants from human activity. Depending on the source, groundwater may need less treatment than surface water in some ways, and more treatment in others. Some wells require disinfection and specific treatment for iron, manganese, hardness, nitrate, arsenic, or other local concerns. In rural America, many homes are not connected to a municipal water system at all. They may use private wells. That changes who is responsible for testing and maintenance. A public utility has trained staff and regulatory requirements. A private well owner has to take a more active role in protecting the well, testing the water, and maintaining the system. So two families living only a few miles apart could have completely different water journeys. One glass may have traveled through a city treatment plant and miles of public pipe. The other may have been pumped from an aquifer directly beneath the property. Weather can change the entire system. During heavy storms, rivers can become muddy and carry more debris and organic material. Treatment plants may need to adjust chemical doses and filtration. During droughts, reservoir levels can fall and source water quality can shift. In cold parts of the country, frozen ground and temperature changes can increase the risk of water main breaks. In hot, dry areas, summer demand can jump because of lawn irrigation, pools, and outdoor use. Water utilities have to plan for all of this while still delivering the same basic result every day. Turn the tap, get water. And water use in the United States can be surprisingly high when everything is added together. Showers, toilets, washing machines, dishwashers, cooking, cleaning, lawn irrigation, car washing, pools, businesses, factories, schools, restaurants, and hospitals all depend on water. A single person may not feel like they use much, but multiply daily use across a city of hundreds of thousands or millions of people, and the volume becomes enormous. Treatment plants and distribution systems are designed to move quantities that are hard to picture. We notice the glass in our hand, not the millions of other glasses, toilets, sinks, sprinklers, and fire hydrants connected to the same network. That is also why conservation matters, especially in water-stressed parts of the country. Using less water can reduce pressure on rivers, reservoirs, aquifers, treatment plants, and energy systems. Fixing leaks matters more than many people realize. A small toilet leak or dripping fixture can waste water day after day without looking dramatic. It does not create a movie scene. Nobody calls the news. It just quietly adds to the bill and keeps wasting water while everyone ignores it. Water conservation is often less about heroic sacrifice and more about fixing boring little problems. Energy is another hidden part of the story. Water is heavy. Moving millions of gallons uphill across long distances through treatment processes and around a city requires energy. Pumps use electricity. Treatment equipment uses electricity. Some systems must move water over mountains or across large regions before it ever reaches a local network. So saving water can also save energy. The relationship works in the other direction too. Producing electricity often requires water. Water and energy are connected in ways most of us never see when we flip a switch or turn a faucet. Some American cities are also investing in water reuse. Treated wastewater can be cleaned to very high standards and used for irrigation, industrial processes, groundwater recharge, or, in some advanced systems, as part of a future drinking water supply. The idea can make people uncomfortable at first because they imagine a direct pipe from a toilet to a kitchen faucet. That is not how properly designed reuse systems work. Water goes through multiple treatment barriers, monitoring, and often environmental or engineered buffers. And if you think about the natural water cycle, water has always been reused. The same water molecules have been moving through clouds, rivers, plants, animals, soil, and oceans for an unbelievably long time. Then there is the question many people ask: is bottled water safer than tap water? There is no single answer that applies to every bottle and every tap. In the United States, public tap water and bottled water are regulated under different systems. Tap water from a public utility is routinely tested, and utilities provide water quality information to customers. Bottled water can be convenient, especially during emergencies or in places with known water problems, but buying a bottle does not automatically mean the water came from a mountain spring guarded by eagles. Some bottled water begins as municipal water and receives additional treatment before packaging. The label matters more than the fantasy. Home filters can also be useful, but they are not all designed to remove the same things. A simple carbon filter may improve taste and reduce certain chemicals, while specialized filters can target lead, certain contaminants, or dissolved minerals. Reverse osmosis systems work differently from basic pitcher filters. The important point is that a filter should match the actual problem. Buying the most complicated device in the store because the box looks scientific is not a water treatment strategy. And filters need maintenance. An old cartridge that should have been replaced 6 months ago is not performing a heroic public service under your sink. One of the smartest things people can do is learn about their own local water instead of assuming every city is the same. Public water systems provide information about where their water comes from, what has been detected, and whether the system meets drinking water standards. Local issues can vary widely. A city using mountain reservoirs has different challenges from a farming community using groundwater. An older neighborhood with aging service lines may have concerns that a newer development does not. Water quality is local, and the plumbing between the street and your glass matters too. The people running these systems rarely become famous, but their work is constant. Treatment operators may work overnight, on weekends, during storms, and on holidays. Laboratory staff analyze samples, engineers plan upgrades, maintenance crews repair pumps and valves, construction teams replace old mains, emergency crews respond to breaks when everyone else is asleep. If the system works perfectly, the public reaction is usually silence. Nobody wakes up, turns on the sink, sees clear water, and sends the utility a thank you card. Reliable water is one of those services that becomes visible mostly when something goes wrong, and that might be the strangest part of the whole story. A modern American city can have hundreds of thousands of people living stacked in apartments, spread across suburbs, working in office towers, eating in restaurants, filling swimming pools, running hospitals, fighting fires, and washing millions of dishes. Yet clean water appears at all of those places through a system most people never see. Under the pavement is a second city made of pipes, valves, pumps, tunnels, meters, and storage tanks. Above ground, life looks normal. Below ground, an enormous mechanical circulatory system is working every minute. So the next time you fill a glass at the kitchen sink, look at it for a second before you drink it. That water may have fallen as rain hundreds of miles away. It may have collected in a river or reservoir, passed through a screen, been mixed in treatment tanks, settled, filtered, disinfected, tested, pumped into a transmission main, stored in a tank, pushed through neighborhood pipes, measured by a meter, and finally sent through the plumbing behind your wall. All of that happened so you could stand in your kitchen and complain that the water is not cold enough. And once the water leaves your faucet, the story is not even over. After you drink it, wash with it, flush it, or send it down a drain, much of that water enters another hidden network, the wastewater system. Sewers carry used water toward treatment facilities where it can be cleaned before being released back into the environment or reused. Eventually, some of it may return to rivers, groundwater, or reservoirs and begin another journey. The faucet feels like the finish line, but in the larger water cycle, it is really just one stop. That is the full trip from river to faucet. It starts with geography and weather. It depends on chemistry, biology, engineering, electricity, gravity, maintenance, public health, and a ridiculous amount of underground plumbing. It works because thousands of individual systems and decisions all have to cooperate, and most days they do it so smoothly that we barely notice. This is strange America, where even the most ordinary parts of daily life can become pretty strange once you look underneath the surface. The next time you turn on the tap, remember that you are not just getting water. You are opening the end of one of the largest invisible systems in your community. And all you had to do was move a handle about 2 inches.